Welcome everyone. I hope you're having a great conference, and I'll try to make it even a little better for you. My name is Oleksandr. That's Ukrainian spelling for Alexander, so you can call me Alex. I work at Snap for 5 years on augmented reality technologies, and I think it's one of the most exciting applications of C++ that we have now. Before that, I participated in competitive programming for about 10 years. I started with Pascal in high school, but switched to C++ in the university. And after some time, I became less interested in competing, but more in implementing algorithms in a generic and reusable way. My favorite topics there were string algorithms and computational geometry. The latter one is one of the main inspirations for the work that I'm presenting today. Now the structure of the talk is on your screen. Most of the time I'll be talking about expression templates. And in here I'll be honest with you, like some parts of the talk contain no radically new ideas, but in my opinion, their potential is severely underutilized nowadays. So it's worth talking more about them. And I believe I made some minor improvements even here and there. And after that, we'll talk about customization. The source code supporting this talk can be found on GitHub using this link. But yeah, I'll say right away that not everything is implemented there. In particular, ranges support is very limited now because I was focusing on implementing the core functionality first. And I'll try to take a couple of questions after each section. And if you need to refer to the slide, there's a slide number in the corner. And as promised by the title, I'll touch a lot of STL algorithms in the process. But I'd like to disappoint rotate fans because there will be no rotate, fortunately. Okay, let's start with motivation. And I think computational geometry is a good example of challenges that I saw in customizing advanced algorithms. Why is that? Well, the first reason is that there's no single correct way to compare floats. And if you try to use the equals for that, you probably saw a compiler warning similar to the one I have here. So you have to use either absolute error or relative error or combination of them or some even more advanced, more numerically stable methods with some threshold. And even if you choose the method, after that, you may need different threshold for comparison in different places in the algorithm. Sometimes you may need more precise types for a part of computation. So say switch from float to double. And in some cases, it's possible to do part of the computation purely in integers to avoid all the precision issues. And this is often the case in competitive programming. Okay, microphone a bit. So in case you're using integers, you have to be careful to avoid overflows, especially during multiplication. And you may need to cast to a larger int type. And when you perform division, likely you need to get a floating point result, so you need to cast before that. This gets us to a point where basically all the basic operations such as comparison, multiplication, and so on are all become customization points. And in STL algorithms, the common case is to have just one customization point and more rarely two. So how this problem solved in industry? Well, the best example that I found was in CGAL, which is unsurprisingly computational geometry algorithms library. And in here, we're looking at an example of two-dimensional computation HAL algorithm. And as you see, after the iterators, it takes some traits class. And what we get from the single traits class are all the customization points that I highlighted. In this case, there are at least 3 operations for determining equality, left turn, and so on. And if you wrote it in a way that STL algorithms are implemented, we would need to pass all those operations separately into the algorithm. So, and this was a very reasonable approach, very practical, but still I was looking for something more elegant. And this gets us to expression templates. Actually, I'll return to the customization only at the last section of the talk. And first we need to build up some material together. So I'll start with a mandatory introduction to expression templates. And as a motivating example, we can use vector addition where we have 3 vectors and we compute their sum. And in a straightforward implementation, we would have operator plus that would take 2 vectors and return a new vector with the elements equal to the sum of the elements. But there is a problem in here because the first plus in the expression actually results in temporary buffer allocation. And I highlighted the line where it occurs, where we allocate the resulting vector. And this is not optimal. So all the linear algebra libraries were looking for a solution to this. And it was found in the form of expression templates. And I think they are used in all the linear algebra libraries we have today. But first, they were introduced in 1995 by Todd Feldhuisen. Excuse me if I mispronounced the name. Or at least this is what the internet told me. And an example of expression templates you see on the left in the form of vector sum expression class. And the idea is very simple. This class just contains the arguments, or typically the reference to the arguments. And then it has some basic vector interface, like it can compute the size as the common size of its arguments. And it has a square brackets operator, which returns its element. Now, the important idea here is that when we construct this class, there's absolutely no computation happening. And only these square brackets operators actually compute something when we ask for it. And on the right, we now modify our plus operator. And instead of returning a vector, it returns this vector sum expression class object, which again just stores the arguments. Now, if we get back to our example, we see that the right-hand side now has not a vector type, but this a bit complicated expression type. And in here, it's important to mention why are they called expression templates? Because the arguments have to be arbitrary types in order to support nested expressions. And in here, we have a nested expression of sum inside another sum. The actual computation is triggered only by the vector constructor. In here, it's indicated by the equal sign after sum. And what we get is equivalent to the for loop you see at the bottom. So the machine code can be equivalent to the code that we would write manually ourselves. But the notation of just adding 3 vectors is definitely nicer. So also, this technique can be called lazy deferred evaluation. And one important thing I'd like to mention, so the main goal is here to avoid temporary buffer allocation and also avoid one memory pass along this buffer when we compute the final sum. But I don't want to create an illusion that this is a free optimization, because in fact you pay for it with the binary size, with this with the equivalent of this for loop that's included on this slide. Now, the interesting question is, are there any expressions in the C++ standard library? And yes, I'll use the expressions and expression templates interchangeably. And remember, they were invented 25 years ago. And I can be mistaken, but looks like the first examples of this appear only in C++20 in the form of view adapters from the ranges library. So in here, I have underlined some of the views that create expressions, like filter, transform, take, and so on. And this is a very important step, because previously, algorithms could be applied only in sequence, one by one. And now such algorithms can be computed into a single expression. So for example, when the first range is created, no computation is performed. But when we actually try to output it into the terminal, the expression is evaluated only at that point. And both filter and transform are evaluated together. Now, one of the things I'd like to highlight in these examples is this kind of a hidden square function in the middle of other syntax, which is passed to use transform. And I think it's kind of too verbose to specify it in that way. So I was looking for a better solution. And yeah, so one other limitation that we have is that we can't transform two ranges together. So in here we have a square, but we cannot add two vectors like in the previous example. Well, at least in the part of the ranges library that was standardized. So that's all for the introduction. And let's see if you have any questions. Oh, I don't see any for now. Okay, then let's continue. And yes, if you're in the process of typing your question, don't worry, I'll get back to it after the next session. Next section, sorry. So I was thinking, how can we do this better? In particular, how can we design operations to support expressions more naturally? And in the standard library, we already have things that potentially could help us. In particular, function objects like plus and so on. So they look nice, but their functionality is quite limited. In particular, I'd say what we can improve is that these function objects can be passed to algorithms, but don't really help to compose the algorithms. And the other point, we know that std plus is implemented in terms of operator plus, but it doesn't really help to implement operator plus for our own custom type, such as a vector. So let's try to address this. And to confirm that this is a problem, if you take basically any linear algebra library, for example, Eigen, it rolls out its own versions of such function objects. In here, you see an analog of plus, which has first the same function call operator, which just calls plus for scalars. But it's important that it also needs an extension for SIMD types. In here, they are called packets. So there's an additional function for that. And in addition to that, we have wrappers to support vector operations, which operator plus calls eventually for vectors. And in the same way, we have function objects to wrap like all the functions we have in math header to treat them in a consistent way. And I think it would be nice to make something like std plus to handle all these cases, or to be extendable to these cases. As a natural extension to ranges, including vectors, I see plus, minus, and so on, all the arithmetic operations applied element-wise, basically like std transform does. For comparison, we can resolve equal to std equal for ranges. And I think the most natural default way to compare ranges is to use lexicographical compare. So how can we achieve this? To build an extensible plus analog with the support for expressions, all the code I need is on this slide. It starts with the Scalar version of add in the Scalar namespace. And inside you see basically the same amount of code that is used to implement std plus. The only difference is that there's additional inheritance from operation. And we'll see what it does on the next slide. And for convenience, we have inline constructs per variable. In addition to that, below, we have a general version of add, which says that by default, it resolves into scalar add by specifying this default formula. But we could potentially extend it to other use cases, for example, to ranges, matrices, polynomials, whatever. And I think a nice name for it would be universal function, which is used for a similar concept in NumPy. So I'll call it this way. And on the right, I'll have universal operator plus and plus equals, which all they do is call this universal add function object and just pass its arguments there. So these operators are truly universal because you can pass literally everything to them. So you don't have to implement them anymore in your library. Of course, there are constraints, and your types must opt in into this behavior by specifying some traits, which are checked by Svina expression. And for now, you either get all the operators or none of them. And I'll think how to improve this behavior to specify only a subset of operators that you need. This is the future work. One of the important things I'd like to note in the implementation of operator plus equals is that there's in-out wrapper around the first argument. And all what it does is to highlight that this argument is used as both an input and output, unlike in a regular plus. Now, to implement these operations, we use function objects, not functions. And the first benefit is demonstrated on this slide. And here we have the implementation of base operation, and it's using curiously recurring template pattern. And to confirm that it's the case indeed, I have the implementation of derived method in the corner. And what it achieves by that is that it's used to simplify the implementation of our operations by adding some functionality from the base class. In this case, this functionality is function call operator on the line 4, which again takes arbitrary arguments. And on line 5, the important condition starts. First, we check if there are no output, like no input-output arguments among them. Then we immediately create expression and don't do anything. Otherwise, we actually evaluate the result into this output parameter. And in here, I'd like to highlight line 8. This is the point that allows the extension to arbitrary types. We basically resolve overload of, for example, our universal add into a scalar add or range element-wise add or whatever. Also, this line can leave the operation unchanged. After that, in line 9, I have a check that there's only one output parameter, and likely I'll need to revisit this assumption to support swap, but for now I kept this to simplify the implementation. Okay, so after we have such operation add implemented, we can return to our first example with vector additions. And in order to support that, all we need to do is, well, first implement our vector. After that, we need to show these universal operators are found via argument-dependent lookup. And we can do this, for example, using an empty base class from the namespace with these operators, like it's done in Boost Operators library. Then we need to implement an operation that applies a given scalar operation to the vector element-wise. And this is just a single implementation to handle all the scalar operations. And you can think of it as something similar to views transform, basically the same idea. And next, need to write a rule that resolves universal operations that are scalar by default, or we can have a trait to identify them. Do this element-wise operation if the arguments are vectors. And again, you can do this only once for all the scalar operations. Okay, and now let's get back to some implementations details I skipped before. First is the input-output parameter wrapper. I think this is a simple utility that, in my opinion, can greatly improve the code readability, but it would be a topic for a separate talk. So for now, let's view it as a basic wrapper, and which just stores the argument or the reference to the argument. And its main purpose to distinguish such cases as operator plus and plus equals. Next is the overload resolution. Again, it wasn't the focus of the design so far. The main purpose is to distinguish scalars from ranges, from tuples, and later from other types. So the current implementation uses template class specialization, but maybe I'll need to change it to regular overload resolution. One important thing I'd like to mention here is it looks like the notion of major argument is useful. What I mean by that, suppose we have arguments. First one is vector of tuple of ints, and the second is tuple of ints. Then obviously the major argument here is vector. And on the other side, if you have tuple of vectors and a vector, the major argument is the tuple. Why is this important? It's important in case we want to support broadcasting, which I think is a very useful feature that can improve performance in some cases. In particular, if you have plus between a range and a single element, we can combine this single element with each element of the range and get the range in the result. Alternative would be to create the range with this element, but it would waste one allocation, which is not optimal. Now let's get to the core of the design, the expression implementation. And it's actually very short. So on the first line, you see that it depends on the operation and the arguments. Let's skip line 2 for now. And all the expression does is just stores the argument on line 3 in the tuple. And the operation is also stored because operation can have some state as well. On line 6, we have a constructor. And unlike some libraries that I saw, I don't always store references. If I encounter temporaries, they are moved inside. On line 8, you have an utility to access the operation. And now let's get back to line 2. In here, I also use the curiously recurrent template pattern. And the important part here is the second parameter, which is the result tag for this expression. It can be a scalar tag. In that case, we allow implicit conversion from the expression to its result to make writing code easier. It can be a range tag. In that case, we would like to inherit our expression from, for example, boost range facade to add some of the range interface to it. And we'll see one more important use case for it later in the talk. And the most important operation for expressions is its evaluation. For that, all we need to do is first resolve the overload for the operation, similarly as I showed before. So from universal add to, for example, scalar add or ranges add. And after that, we just apply the resolved operation to the stored arguments. And since the arguments can be expressions themselves, well, before that, we of course need to evaluate them first. That's kind of all we need. An important topic for expressions is their optimization, which nowadays compiler mostly do for us. It can be like canceling identical terms, simplifying identity operations. One interesting case is in SIMD, multiplication and addition should be used into a single FMA operation, which is a special instruction to optimize this use case. And for more dedicated optimizations, I'd recommend a talk from today called Algorithms from a Compiler Developer's Toolbox, which was a great talk with some great examples of other optimizations you could do. So yeah, that's all for the implementation. And now we're ready to go into the examples. Let's see if you have any questions. Okay, looks like no questions so far in the Q&A. So let's continue. So if you get back to the ranges example we saw before with the square operation, we could rewrite it by just applying square function object to the range. And at the first sight, the syntax may not be like immediately clear, but it's used in all the linear algebra libraries for vectors and for matrices. And I didn't hear about any problems with this, so I think we could expand its applicability to any ranges. So you see the whole construct with views, transform, and lambda inside it is gone. Another feature of ranges library is projections. For example, for the equality, you can specify two projections that are applied to input ranges before they are actually compared for equality. So, for example, if you want to compare elements, but not the elements themselves, but their absolute values into ranges, you could specify projections in form of lambdas, like I wrote here. And actually, this example highlights the point that it would be useful to have all the math functions as function objects as well, in order to avoid this simple lambda wrappers that we have to write. And to be honest, I think projections overcomplicate this interface for equal. And with expressions, we could achieve much shorter notation, which does exactly the same thing. One limitation is that currently, unlike in Ranges library, like member projections are not supported. But I think I can use an idea from Boost Lambda library to support that as well. Now, in order to unlock the potential of expressions even further, it's useful to have fold operations. So in the standard, we already have std accumulate and std reduce. And with a bit of luck, we could have ranges accumulate, but unfortunately, it wasn't included in C++20. But I'd really prefer to have a syntax, something like this, where the idea is to have fold as an operation that takes another operation as an argument. In this case, we could write aliases for common cases, such as sum is the fold over addition and product is the fold over multiplication. We could also resolve min and max for ranges into respectively fold over min and max. And this is consistent with the overload of std min for initializer list that we already have in the standard. There are also special case of short circuit in fold, which could be implemented in a special way to be more optimal. But conceptually, things like all off is just a fold over logical AND, and any off is just a fold over logical OR. Now, let's see what we can do with this. And let's look at the examples outside just vector arithmetic. So in C++17, we got fold expressions with specific syntax. But if we make our fold operation constexpr, I think they can be replaced with just a function call syntax. So we don't need special language syntax for that. And also, standard fold expressions support only operators, like plus operator, comma, and so on. But in here, we could use any operation, and in particular, it would be useful to have min and max to fold over them. Next, if you look into count, and for example, we need to count elements equal to 0 in a range. What we can do is start with the equality of range in 0. And in here, again, I'm using broadcasting because I'm comparing 0 to each element in the range, so I get the Boolean range. After that, I cast it into int just to be explicit about this. And I compute sum of that. So in here, you see that the std count can be expressed as a composition of several simpler expressions. Next, suppose you'd like to convert string into lowercase and do it in place without new memory. Well, you could do this by just calling to lower and wrapping the string into in-out wrapper. And if you want to check if a string is all lowercase, you just write all of is lower s. And again, this doesn't allocate temporary buffers. These are all expressions. And if you at some point decide to extend hash to work on ranges, then I'd say that hash for a range is a fold over some hash combiner, like boost hash combine, for example, of hash applied element-wise to the range. So we could write such overload resolution rule. And looking at the slide, I think this is the level of expressiveness C++ should have. And unfortunately, it's not supported in the current standard. But I think in the previous section, I showed you that it's quite simple to achieve this. Now, an interesting question is, before that, we looked only at the ranges, but are expressions actually useful for scalars? Well, the first obvious use case are short-circuiting operations. For example, in logical OR, if the first argument is true, you don't need to evaluate the second argument at all. But there is a more interesting example. This is a modular arithmetic example where you have some modulus. Let's say it's a prime number around 1 billion. And you want to evaluate some expression with that modulus. So without expressions, suppose you have like type to wrap your numbers, which applies this modulus every time. In that case, you would need to apply remainder operations 3 times. And this is comparably expensive operation to do. But if you have expressions, then you could note that actually you can cast all the arguments into int64 type, sum them all together inside brackets, and take the remainder only once after that. And we can do this because the sum in the brackets is guaranteed to be less than the maximal uint64 value. And in fact, you can sum up to 18 products to fit into this value. And actually, this expression is a very important use case because it's a special case of dot product that is used, for example, in competitive programming to multiply matrices. And this optimization to reduce the number of remainder operations is very important there. Okay, so that's all for this section. Let's see if you have questions. Okay, let's look in the chat. Yeah, sorry, member projection is not supported. I meant in my implementation. Okay, there are some comments about fault proposal. I guess I'll read it after the talk. So let's continue. Now let's think. Let's recall a formula from some basic calculus for the derivative of cosine, and it's just minus sign. So how would we currently implement this function? Well, it can work for any floating point type, so it's natural to make it a template, looking something like this, and we should probably add the concept that applies only to floating points. But what I'd like to note in here that all the important information in here is inside the return statement. So wouldn't it be nice if we didn't have to write all the other boilerplate code that we have here? For example, if you could define our function this way. Now, let's think what's written in here. Well, normally expression templates expect some kind of values as their arguments, like vectors and so on, or other expressions based on vectors. But suppose we remove that limitation and also allow other function objects as parameters. So in this case, in the first option, we have just minus sign. Sign is a function that takes one argument and returns one argument. And minus is the negation operation, which also takes one argument. So I think it's natural to interpret this notation as a function that takes one argument, passes it to sign first, then passes the result to minus. And the second option kind of makes it more explicit. Here, x underscore denotes that we have a function of one argument, and x is this argument. And I'll get back to its implementation in a short. And yes, indeed, this syntax works in my library, and you can apply this function to like doubles. And if you extend sign and negation to support ranges, you could apply this function to ranges as well. So since in here we have an expression, but with operation arguments, I'd propose to call this an operation expressions, and I'll refer to other expressions as value expressions. Now let's look at an even weirder example. Suppose we'd like to multiply plus by minus. What could this even mean? Well, we could recall that both plus and minus are binary operations. So we could rewrite it in this way. And again, LHS and RHS are special things to indicate first and second arguments to the binary expression. And yes, I impose a constraint that if you have kind of two leaf operations in the expression, they need to accept the same number of arguments, in this case too. And if you recall some basic calculus, then we could also rewrite this as a difference of squares of arguments. And indeed, all these definitions are equivalent, and you can use this as a normal binary function. So in order to avoid some confusion, I'd like to show how things like x underscore are implemented. In fact, there is nothing special about them. They're almost like regular operations, but all they do is return the argument with index I out of n input arguments. That's all they do. And in line 12 to 14, you see some convenience aliases for them for the case of unary and binary functions. And I'm not sure about the naming style in here. I just added underscore at the end to distinguish them from local variables. And yeah, I'm fully aware that there are existing implementations of a similar thing. And even we had one since early 2000s in Boost Lambda, which provided 3 placeholders. And the more modern version is in Boost Yup with a slightly different syntax. So they both have nice support for operators, but for other functions, they need some more boilerplate code. And in the app, I think you need to wrap the result into like make operation or something to actually get it as a function object. So what's interesting, in my library, these placeholder operations are treated absolutely in the same way as all other operations. Now let's continue to finish the implementation of this. What we need to do, well, remember in the definition of expression, we had this CRTP pattern going on with the result tag specified. So we can specialize this expression base for operation tag and inherit it from our base operation to add function call syntax to it. And what it does, when we pass arguments to such expression, we need to pass the same arguments to all the operations inside this expression before evaluating it. And I have almost complete code to do that below. So on line 2, we have this pass arguments function, which takes an operation and the arguments. Then we check if this is not an operation. So we went down to some leaf which contains some value like a number. Then we just return this number. Else, if you actually have an operation, then if it's an expression, then we need to recursively pass the same arguments to all the children of this expression. And if it's not an expression, we just pass the arguments to the operation. And surprisingly, that's all the logic we need in addition to the expression framework I described before. Okay, it looks like there are finally some questions popping up in the Q&A. So let's look into them. Ideas for expression templates for chained operations on non-scalar, which is general, are not element-wise, e.g. you have expressions with matrices and some operations work independently of coefficients. This is easy. But some work on tiles, small submatrices, while other even work on overlapping subtiles. Even. Okay. Well, I think this kind of more relates to the evaluation, to efficient evaluation of such expression. So I don't see any problem in just writing this expression where some operations are element-wise, some of them are more complex. So yeah, this is more in the topic of executing them in the most efficient way, probably. Yes, but for clarification, you can find me after the talk. Regarding your example on scalar expressions, optimizing modular operations, is it reasonable to expect an aggressively optimizing compiler to inline and eliminate the modulus, especially if the large prime is known in compiled time? I think at some point I tested both options in competitive programming problems, and this modulo wasn't optimized the way, at least inside matrix multiplication. But maybe compilers advanced after that and could do this. Next question. The compiler might optimize, yes, but still you have to write error-prone remainder operation. Okay, just comment to the previous question. Okay, now let's continue and let's see what we can actually do with what we have. We can start with implementing even some basic operations in terms of others. For example, on line 2, you see that square is just the argument multiplied by itself. On line 6, we can represent greater as less with swapped arguments. So RHS goes first. On line 9, what you see is actually a bit complicated code, but from what I know, it's the implementation of three-way comparison that generates the best machine code. But yes, it's a bit obscure. And on line 13, we can express none of as a negation of any of. And you could note that on this slide, I implemented some operations as structures and some just as constants. the reason for this is that I think that different implementations for some operations can be overridden for special types. For example, for three-way comparison for ranges, you would likely want to use lexicographical compare or something, which is definitely more optimal than this formula. Well, maybe all of the operations should be implemented in a customizable way. But in here, for simplicity, I simplified like greater and none of. Let's move further. Now, if you have this, think lambda expressions from the standard now seem too verbose. So let's look at the example of French transform and compare what we need to write as lambda now and how can we rewrite this using such operation expressions. And I think this is particularly useful in algorithms that expect predicates, for example, find if. In here, you can rewrite condition like x greater than 2 in a much simpler way. And if you get back to the other ranges example that we had, again, we can rewrite the predicate pass to use filter. And also, if we implement toString as a function object, we could easily pass it to use transform. Now, looking at this, I was thinking about that maybe the syntax is too dangerous because it's too concise. But after thinking for some time, I believe that all we do in here is we remove all the boilerplate, but keep all the important parts. So I don't think readability suffers in any way. Now, there was an interesting abbreviated lambdas proposal, which proposed to replace the syntax on the left with all the manual specification for return type and no exceptness into a much shorter notation on the right. And there were even two options, one of them even shorter than the first one. So unfortunately, this proposal was rejected. But to everyone disappointed by this, well, rejoice, as now you know that we can achieve even shorter notation using only existing language features. Well, with the exception that we can't call member functions on A and B, like in this example, this nicely. But you can call any kind of free function. And you can create like a wrapper that would call this member function. Now, another thing I would like to look at is that in the standard library, we have a bunch of algorithms that end with if suffix and like some other variations of it. So why do we need them? Well, if you look at the ranges find if, it takes a range and the predicate. And ranges find takes a range and a value. And why there are two of them? Well, because in order this search of a value is a very common use case. And I think currently the most concise way to express it in terms of find if looks something like this at the bottom. And I didn't even include no except in there. So it's reasonable that we don't want to write this all the time. So we have ranges find for that. But with the syntax I'm proposing, well, I think we could replace find if with just find, which takes the predicate. The old find, which searches for a value, we can rewrite as x equals value. Find if not, we can rewrite by just negating the predicate. And there's also this quite interesting function called find first of, which is likely not very obvious what it does, but it actually takes two ranges and searches for the first occurrence of some element of the second range in the first one, And I think current notation isn't really expressive, and we could introduce another function called isIn, which checks if an element is in the range. And we could pass it to our new universal find. And there is a find first of with additional predicate. And well, we could just apply this predicate to the range, creating an expression. Now let's look at another example of binary search. And I'd like to be honest, every time I need to call one of the lower bound and upper bound functions, I need to spend some time thinking which one to call and how to do that correctly. But if you just write down their definitions on the right, we could see that we could implement a function called find first. Then, and it will look at the arguments. So first we need a wrapper to indicate that the range is sorted, which I show in here as sorted range. So find first will look if the first argument is a sorted range, and the second one is the predicate of the form like x greater than equal to some value. It can understand that we're intending to call lower bound and call that behind the scenes. So again, I'm not claiming that I want to re-implement lower bound and upper bound, but I think this is a nice user interface to access them. And the same actual algorithms are called underneath. So that's all for this part. Let's see if you have any questions. Does the predicate x equals y hold the y object by value or as a reference? Well, as you saw on the slide with the expression implementation, I take forward the references and forward them to store inside the expression. So this just depends on how you pass y. If you pass by reference, it will hold reference. If you pass it temporary or move it, it will hold the value. Okay. Okay, looks like no more questions, so let's continue. Now we actually get to the customization part, and we'll start with the policy design for operations. And the motivating example for me was comparing two vectors that store another vectors, like geometrical vectors from GLM library, for example. And you want to compare them not for exact equality, but with some threshold. So a straightforward way would be to write a code like this, which goes through the range and compares all the coordinates. And we can simplify it a bit using range algorithms. But for that, we need to first implement this compare vectors function that actually compares our GLM vectors with the given threshold. So this looks better, but still I'd like to say that this code doesn't exactly express the intent that I have. My intent is not to pass two vectors with some comparison function into this algorithm. My intent is to take these vectors and compare them as regular vectors, but when I get down to the scalars, I want to apply this threshold for comparison. So what I'd propose as an alternative syntax is this one. When we call equal, after that we have the way we want to compare scalars. In this case, it's an absolute error with the threshold. And the arguments are on the right. And what's important in this notation, it clearly separates all the different parts we have in here. First, we have the operation. After that, we have specific way how to perform this operation. And the arguments are clearly separated from all of this in the round brackets as they should be. And of course, we could extract this specialized operation into a function object and call it as a regular function after that. And such syntax supports specifying multiple policies, which results in the composition of policies. So first we have an operation, then we have pipe operator, which I chose for no particular reason, just because it's popular in the ranges library. So I may think of a better syntax for this. But the idea is that we have an operation, and after that we can have multiple policies that somehow affect this operation. And to give a more precise definition, policy is an object that changes how certain operations are performed. And this means that it leaves all the other operations as they are. And we can look, for example, at the absolute error policy on line 2. On line 3, it somehow identifies itself as a policy. The exact mechanism is not important. On line 4, we have this stored threshold we'd like to use. And the important thing here is to know that such comparison policy, it affects not only equality, but it should affect all the other comparison operations. That's why on line 8 and 9, I specify how this policy affects equality. It just checks if the absolute difference of the arguments is less than the threshold. And on line 12 and 13, I specify it for less operation in a consistent manner. And it's interesting to see how many objects in C++ follow this definition. And the first one we can find in some compilers like GCC and Clang is fastmath compilation flag, which includes a bunch of other flags. And the idea is here is to optimize some floating point operations by ignoring some corner cases that they can have. So I'd say that this is a policy that affects these floating point operations. And the problem with this is that once we compile the code, we can't access other versions of things like math square root. So we can't call it in the same function once without this flag and once with this flag. Next examples we can find in range algorithms, for example, in equal algorithm. And in here we have even two policies at the same time. At first, we have execution policy that affects how we process the ranges. And it's supported by multiple range algorithms and can have sequenced and parallel values. And then we have binary predicate that affects how we compare range elements. So the problem I see in here is that these policies are mixed with the actual algorithms of the equality. And we have one at the start and one at the end, which is not nice. So what I propose is to clearly separate them. So we have equal, then we specify range processing policy, and then element comparison policy. And actually the order isn't important here. And if you want defaults, we don't need to specify anything. And we can specify just one of them. And the actual arguments, the range iterators are separate in the round brackets. Next example we can see in random header, where we have generators that specify how the uniform random bits are generated. But I've read an article which criticizes this library and mentions some missing customization options. First one is which algorithm is used for uniform distribution. And this is important because it kind of affects portability of your code on different platforms. And the second one is that there is no way to specify how random device is seeded. And we could solve all of this by composing multiple policies and passing them into these distribution algorithms. Another interesting example is allocator. And I think we could say that allocator is a policy that affects allocate and deallocate operations in some consistent way. Why is this interesting? Well, for example, we have vector class in the standard, and it has this allocator parameter, but also it has one missing customization option. You know, when you try to push back a new element into the vector and there's not enough allocated space for it, vector reallocates itself. But when it does it, it actually multiplies the current size by some factor so that we have like amortized constant complexity in the end. And this is kind of a hidden option. Compilers usually set it to 1.5 or 2. And it's totally reasonable why it's hidden, because like no one would like to have even more template parameters or even more constructor parameters in the vector to specify such minor customization detail. But we could easily solve this by introducing some growth policy and composing it with allocator policy into a single policy. That is totally optional, but advanced users can pass it to the vector. Now, if you get to the data structures with even more template parameters, one of the extreme cases now is unordered set. It has 4 template parameters. The nuance in here is that hash and key equal, they have to be consistent for this data structure to work. But the interface doesn't enforce it in any way. So I'd say the problem current interface has, first is that there are too many template parameters. And if you think that's not a problem, well, wait for the next slide with the next example. Also, in order to specify custom allocator, we need to also specify all the template parameters before it, which is kind of too verbose. And the most important problem, in my opinion, suppose we implement specific hash, which requires not the default equal to, but some other custom comparison. Then for the users of this hash, it's very easy to forget to specify this alternative equality as key equal. And the code might compile just fine after that. For example, hash compares strings ignoring the case, but we forget to pass corresponding equality. The code will compile and run, but it won't work correctly. And I see a solution to this as introducing hashing policy that consistently affects hash and equality. This way, implementer of the hash needs to implement such policy only once, and it can be passed to unordered set by its users as a single object. And even more, we can compose this hashing policy with the allocator. So we'll have just 2 template parameters in an ordered set. And now let's look at a more interesting example of a data structure called trip, which is used in competitive programming. Just to give you an idea, this data structure can represent an array, and it supports arbitrary slicing and concatenation. it can reverse a subarray, it can query a subarray with a predefined query, for example, to compute the sum of elements there. And it supports predefined modification of a subarray, for example, increment of a value. And all of that operations are in logarithmic time. To make that work, there are actually a lot of customizable operations. First one is obviously allocation. Then we have some random numbers involved. We have these queried values and modification values that should be combined together, reversed, and so on. So in total, we get at least 9 different operations to support that. So if you follow the implementation style of unordered set, we'd end up with a class with like 10 template parameters and as many constructor parameters, which no one would like, I think. But the thing here is that a lot of these operations are actually dependent between each other. And on top of that, we could also pass policy to affect any of those operations, which is a composition of other policies. So that's all for this part. Let's see if you have any question. Okay, I see that applying a policy looks similar to the proposed std prefer, std require that can be used to configure executors. Your pipe operator looks nicer to me than std require. That's an interesting point. I think I should read that proposal. So yes, thank you for letting me know. Now let's get to the last part where we finally address the question that we started from. So how do we customize advanced algorithms? And in here, I will look at the example of a simple geometrical algorithm to project a point onto a plane. Well, my first attempt at customizing this, at the time I already had this idea about policies to affect operations. And following the style of execution policy in STL, I passed this policy as the first optional argument to all the functions. And as you see, I had to manually pass it to each of the composing functions. And this actually worked, but this manual policy passing doesn't look nice. And yes, actually, this was my first kind of successful attempt. Before that, I had a couple of unsuccessful ones. So this one at least worked in the way I would like. But after working with expressions, I thought about this. So again, on top, we have the same projection function, and kind of details of the implementation aren't important. But what if we rewrite it into an operation expression on the bottom? So on lines 10 and 11, we have just basically an aliases with nicer names for the arguments. On line 12, we have the same expression for t. And on line 13, the final formula for this operation. And yes, this syntax isn't as concise as I'd like to, mostly because of static const expers. But otherwise, it's quite concise compared to what we have. But you may ask, where did the policy go from the previous function? Now, the beautiful thing about this is that if you have this expression represented in a consistent way, then we can automate policy application to all the operations inside the expression. And let's look at a simpler example to understand how we can do this. Suppose we have a function that multiplies the first argument by 2 and adds the second argument. And we expect these arguments to be ranges, so we specified unsequenced policy from C++20 to vectorize this operation. And yes, we pass a couple of vectors in there. And on the right, I have the expression tree for this expression visualized. So how would we process this? Well, it would make more sense to start from the bottom to the top, but typically we have reference only to the root of the expression tree. So we have to start from there. So what we do? We start with add, but first we know nothing about its arguments. So we have to go down into mul. And there we look into LHS. We see that it takes two vectors, so the result is a vector. After this, we know that mul takes a scalar and the vector. This means that it should be resolved into a range operation, and we identify it as element-wise mul. After that, we apply our policy to this operation. And since we have range operation, we can vectorize it. So we convert it into vectorized mul. Now let's get back to the right branch. Again, the RHS results in the vector. Now we know that add takes two vectors. So we resolve it into element-wise add. And after that, our policy converts this element-wise operation into vectorized one again. So the complexity is that we have to interleave overload the resolution with policy application because they may depend on the results of each other. And in the last example, maybe it wasn't obvious, but in fact, the policy can affect the resulting type of the operation. On the previous slide, we went from element-wise range operation to vectorized range operation, so it didn't really change the type. But for example, if by default we disallow to mix different arithmetic types in the expression, but allow that with a special policy, then if you look at int added to float, in the first case without policy, it results in the compilation error. And in the second case, we have float using like regular C++ promotion guidelines. And these are clearly different result types. So to formalize this algorithm, we start at the root of the expression. And if there are operation arguments, we have to process them first, so we recurse into them. And after these arguments are processed, we resolve the operation. And if it changes, after that, we go back to step 2. If not, we start to apply policies that can be applied to our operation. So each applicable policy we apply, and after that, we need to repeat the procedure starting from step 2 for the operation after the policy. So it's not really a complex algorithm, but still has a couple of separate concerns. And this gets us to the point that in regular C++ templates, what we have is that there's kind of function template. We can instantiate it with some specific type. And after that, the compiler figures out, based on this type, how to overload all the operations that we have. With this approach, what we basically do, even after we injected our type, we need not only to resolve the operation, but after that, we can also replace these operations with something completely different. So this feels like templates, but applied not to the types, but to operations. So there's a natural question, do we really need this feature? So I already mentioned that they had some failed attempts in customizing geometry algorithms. And one of the ideas was that we can achieve similar results by using wrappers. For example, we can wrap float into a threshold compared float that specified that we need to compare them with some given threshold. But there are multiple problems in this approach. First of all, that we may need different threshold in different parts of computation, and it's not clear how to manage this. Next, we need to implement all other arithmetic operations for this wrapper, including operators, math functions, and so on. So a lot of boilerplate code. And also such wrappers introduce unnecessary templates and instantiations of containers if we store such floats in the container. And this is clearly not the intention. We just want to take a regular float and change only how some operations are applied to it. So all of this is a work in progress and design experiments. So there are still a lot of problems and unanswered questions. The main ones is that the lifetime of expression arguments is hard to manage correctly, especially during the policy application process. Also, compilation errors are quite complicated so far. And currently I was trying to implement better support for high-level functions, and Clang gives me like totally useless error and doesn't give any idea where the actual problem is. So, and if anyone is interested in trying this out or implementing some things, I had the link to the library on the first slide. I'll be honest, there's no documentation, and unit tests are quite weak for now, but I think the code itself is structured quite well. And I'd like to say that the fact that all of this can be implemented inside C++ is a great testament to C++ flexibility. But I think operations customization using policies would benefit from having language support. So that's all from my side. Thank you so much for your attention. Okay, so the first question is, you described in the library's ability to create very terse lambdas using placeholders. Do they compile to same binary as C++ lambdas? Well, for now, I didn't check that because I was focused on making this code work as expected. But I don't see any reason not to compile them into the same machine code, because like in the linear algebra libraries, we also have expressions, and they're tested to compile into the optimal machine code. But yes, of course, I'm planning to test that once everything works. Okay, so we still have 5 minutes. I don't see any questions in the Q&A. So let's look at the chat for some time. Okay, see one more idea for abbreviated lambda syntax. Or maybe it was in the proposal, but I didn't fully read it. Okay, I wonder if the following will fail due to aliasing. Replace range, x equals begin range. Yes, I didn't think about the aliasing problem for now. It wasn't the focus yet. But yeah, I saw some ideas on this, for example, in Eigen Library. So I'll get back to that. Would it perform the mutation in place or return a lazy view that produces the result? Well, for this question, it depends on how you pass the argument. If you don't wrap it in out wrapper that indicates input output argument. If you don't wrap it, then it's considered just an input argument. So you'll have an expression or a lazy view. But if you wrap it into in-out, then the mutation will be performed immediately in place. Okay, pointer to the proposal. Just think you'll take a look at this. Okay, so looks like we don't have any more questions. Yes, thank you so much for attending.